In this video, we're going to talk about concentration units, molarity, percent by mass, percent by volume, and we're going to apply some formulas to deal with concentration units and to interconvert between moles and concentration, or even between grams and concentration. First, we have to figure out what concentration means. When we talk about concentration, we're talking about an amount of one substance mixed into or dissolved into a certain amount of another substance to create what's called a solution. So just let's get some terminology out of the way. In a solution, the solvent is the compound, usually water, and almost always a liquid, that dissolves another compound. So water, for example, in salt water, water would be the solvent and the salt would be the compound that gets dissolved, and that would be called our solute. So a solution is made up of a solute compound dissolved into a solvent compound, and we take that mixture, that combination, that mixture, we call that a solution. A solution is made up of a solvent and a solute, and specifically a solute dissolved into a solvent. Now, how do you distinguish between what's solvent and what's solute? Generally speaking, the solute is in much smaller quantity than the solvent. So you might have a mixture, a solution of two liquids. Which one is the solvent if they're both liquids? Well, which one you have less of is generally considered your solute, and the one you have more of is your solvent. Although in practice, even if you have more liquid than water, if you have a mixture with water, water is generally automatically considered your solvent, even if there's less of the water than there is of something else. The mass of a solution is always equal to the mass of the solute plus the mass of the solvent. The mass of a solution is the combination of both. And generally speaking, all but one of the concentration units we're going to use are going to have in their denominator, in the lower part of the fraction, the mass or volume or some kind of quantity of the entire solution. Solute plus solvent, not just the solvent. The volume of a solution is not as straightforward. It depends on whether your solution is made up of two liquids or made up of a solid dissolved into a liquid. If it's the latter, if it's a solid dissolved into a liquid, then we do not take the volume of the solid into consideration. Most of the time, we don't even know what the volume of the solid is. But even if you do, or even if you know that, or even if you have the density of the solid and you can calculate its volume, you do not add that volume of the solid to the volume of your solution. Solids have unpredictable effects on the volume of a liquid when they get dissolved. They can actually contract the volume instead of adding to it. The same is true for liquids, actually. When you mix two liquids together, their volumes are not necessarily additive. Nevertheless, we're going to make the simplifying assumption when it comes to liquids that the volume of a solvent and the volume of a solute add together. So when you want the volume of a solution made up of two different liquids, you simply add the solute and the solvent's volumes together. When it comes to mass, we don't have this problem. Just add the sum of the masses of the solvent and the solute is always the sum of the solution as a whole. Remember, nothing changes the mass of a compound. Mass is unchangeable. Mass is conserved. To form a solution and not just a mixture, and later on we will talk about different kinds of mixtures where the solute isn't really truly dissolved in the solvent. But to form a true solution, the solute must dissolve in the solvent. For example, sand and water don't form a solution. Even though you can drop sand or dirt or other kinds of compounds that don't dissolve in water, you can drop them into water, you can mix them, you can even stir them. And for a very short time, you'll actually see them appear to mix. Or you can take oil and vinegar, shake up the bottle of oil and vinegar in a dressing, a salad dressing, and for a short time, it'll appear that they are mixed, but they are not. This is not a solution. It's just a heterogeneous mixture. And you know that because if you give it just a short period of time, the two different compounds will eventually settle out and separate from one another. A true solution will never separate. You can wait till the end of time, and a true solution will never have the compounds separate from one another. They will always remain perfectly homogeneously mixed. That's how you know the difference between a solution and just a plain old heterogeneous mixture. So solutions are described or quantified by their concentration. One of the main differences between a compound made up of more than one element and a solution that contains two compounds mixed together is that a solution can actually vary the amount of its concentration, and it's still just a solution, a mixture. Concentration is always a compound unit. It always involves the expressing the quantity of solute per 1 unit of solution. Or sometimes, in only one example, we're going to have a concentration unit that is per unit of solvent. This is molality. Molality is the only unit that we're going to see that involves that has solvent in its denominator instead of the solution. And we're not going to make too much use of molality outside of applying it to a very specific type of problem. So for the most part, we're not really going to trouble ourselves with the details of molality. So units of concentration that we will look at, molarity is one of the most important units in chemistry. It's used everywhere and all the time for almost everything. Molarity, not to be confused with molality. Molarity is abbreviated with a capital M. Oftentimes the capital M is underlined, but it doesn't have to be. Usually I try to underline it just to make a distinction there. The definition of molarity, and you are going to use this definition a lot, so don't just take this definition and forget about it. You're going to do your calculations constantly paying very close attention to the specific units that make up the compound unit of molarity. Moles of solute on top and liters of solution on the bottom. So we have two different units. And in fact, because this is a compound unit, we have a way to interconvert between moles and liters. This is a conversion factor. As all compound units are conversion factors, so is this one. It allows us to convert between solution liters and solute moles. And that's going to be very useful to us. That's by far the most common unit of concentration in chemistry, but there are others. Percent by mass, abbreviated percent M over M, is going to be mass of solute divided by mass of solution multiplied by 100. Anytime you involve yourselves with percentages, anytime you've got a percentage, you always multiply the fraction by 100. So percent literally means per 100. You can either use this as a formula, or once again, like any compound unit, you can also apply it in a dimensional analysis kind of fashion to convert from mass of solution to mass of solute. You don't have to use grams. As long as you use the same mass unit or weight unit on the top and the bottom of the fraction, you could use any unit you want. You could do pounds of solute per pound of solution and multiply that by 100. You'll get the same exact percentage. Just remember that the mass of solution is always the sum of the mass of the solvent and the mass of the solute taken together. It's both. Percent by volume is milliliters of solute divided by milliliters of solution. Again, you can use any unit you want. You don't have to use milliliters. You can use gallons, fluid ounces, quarts, pints, ounce. I think I said quarts and pints already. Liters, kiloliters, microliters, it doesn't make any difference. You can use any volume unit you want. Just make sure you use the same volume unit on the top and the bottom. Otherwise, those units will not cancel and you will not get a valid result or your expected result. And as always, you multiply by 100 because this is a percent. These zeros in this line literally mean 100 per 100. And of course, the volume of the solution is going to be the volume of the solute plus the volume of the solvent. These are generally for cases where both the solvent and the solute are liquids. some more concentration units. Sometimes you want to express percent mass over volume. So the top part will be mass and the bottom will be volume. So for example, oftentimes, and this is usually these are the assumed units. Whenever you have a percent mass over volume, the presumed units, if you don't say anything, are going to be grams per milliliter. However, do not confuse this with density. This is not density. Don't confuse this with density. It's not grams of the substance per milliliter of substance. It's grams of solute in a mixture per milliliter of solution, which is a completely different thing. It's the mixture as a whole. This is not density. Density refers to only one compound, not a mixture. So this is grams of solute per milliliter of solution, a completely different thing on the denominator side. So this is not density, but nevertheless, like density or like any other compound unit, you can use it to interconvert between volume of solution and grams of solute. Two more units that we'll make some use of: parts per million, ppm, and parts per billion, ppb. Generally speaking, one way you can do this is grams of solute divided by grams of solution multiplied by a million. This is the equivalent of percent, but instead of per 100, it's per million. So instead of multiplying by 100, you multiply by 1 million, take gram over gram. Another way to express this, and I'll mention this in the notes later, is to take milligrams divided by kilograms. Milligrams of solute. Remember, these are two different things on the in the numerator, the top number, and the denominator, the bottom number. They are two different things. The top is solute, the bottom is solution. These are not the same item. You can't take the mass of solute and put it on the top and the bottom. That wouldn't even make any sense anyway. So kilograms of solution. Notice if we take milligrams divided by kilograms, what is that? That's 10 to the minus 3 grams divided by 10 to the positive 3 grams. That's going to be 10 to the negative 3 minus 3. That's going to equal 10 to the negative 6th, or in other words, 1 over 1 million, which is literally the definition of per million. So oftentimes this is expressed as milligrams of solute per kilogram of solution. That's another way of expressing part per million, just converting your solute to milligram units and converting your solution to kilogram units and dividing one number over the other. Or you can simply take grams over grams and then multiply by a million. Same exact effect. Parts per billion works exactly the same way, except of course, B for billion means you're multiplying by 10 to the 9th instead of 10 to the 6th for a million. Remember, 10 to the 6th is 1 million, 10 to the 9th is 1 billion. That's all you're doing. If you want to see what units you would use to express this, oftentimes it's expressed as micrograms of solute per kilogram of solution. So micrograms, 10 to the minus 6 divided by 10 to the positive 9. Oh, did I say positive 3? Excuse me, I'm jumping right to the result. Sorry. 10 to the positive 3. So we take 10 to the negative 6 minus 3 is going to equal 10 to the minus 9, or 1 part in 1 billion per billion. So that's where these numbers come from. So you can either take grams over grams or any mass unit divided by any of the same mass unit on the bottom and multiply it by the actual number, 1 billion. Or you can simply take micrograms divided by kilograms, which amounts to exactly the same thing. But if you're going to do it this way, or if you're going to do it this way, remember, don't multiply by a million. You've already got the million and the billion built into the units that you are using. But if you're simply going to take grams or pounds or whatever other unit you're talking about, if you're going to take those units, then multiply by a million and a billion respectively. And finally, we have molality, abbreviated with a lowercase m. This is one way you know the difference between molarity and molality. Molality with an L is designated with a lowercase m, and it's moles of solute per kilogram of solvent. This is the only unit that uses solvent in the denominator instead of solution. It's more of a ratio of solute to solvent than it is an actual concentration. It's more like a ratio. For the most part, we're not going to deal with much with molality except as a given quantity. Okay, let's start doing some examples. We're going to start with molarity. It's our most important unit as far as concentration goes, just because it's the most widespread in chemistry. I want to make a saturated saline solution. Saturated simply means that the solvent, water in this case, is holding the maximum amount. It's dissolved the maximum amount of solute that it can. And it cannot hold any more solute. It cannot dissolve any more solute. There is a limit to how much solute a solvent can actually dissolve. And it's specific for every kind of solute and every kind of solvent. And it also is related to temperature. And we'll see that later. Anyway, I want to make a saturated saline solution. Water can only dissolve about 36.5 grams for every 100 milliliters of water that you have. I dissolve 115 grams of sodium chloride of salt. Saline, by the way, means salt, in case you don't know. Saline means salt, table salt. When I say salt, I mean specifically sodium chloride, into 300 milliliters of water. What is the molarity of this solution that I just made? So remember, molarity equals moles of solute. We're just going to apply the definition. We're going to convert. If we don't already have the units that we need, we're going to convert to the units we need to fulfill the definition of molarity. Then we're going to plug those numbers in. Moles of solute per liter of solution. Okay, well, what are moles of solute? Well, we don't have moles of solute. We have 115 grams of solute. So we're going to have to convert. We're going to convert 115 grams of NaCl to moles of NaCl. So every 23 grams of NaCl gives us 1 mole of NaCl. So by this way, we convert to moles of NaCl, which is going to be 115 divided by, not 23. 23 plus 35.5 is 58.5 grams. So 115 divided by 58.5 grams of NaCl gives us 1.966 moles of NaCl. That's the number that will go on top. And then how about liters of solution? Now remember, I said that the mass that we add to the solution, we're not going to count the solid, we're not going to try and guess or figure out the effect on the total volume of our solvent by adding solid. Since this is solid, we're simply going to take the volume of our water as the volume of our solution. Since this is a solid that's being added to the water, we're not going to try and figure out what the effect of the solid is. We're just going to make the simplifying assumption that the solid has no effect on the volume of the solution. And for small amounts of solid, that's generally true. There's no significant effect. Okay, so we have 300 milliliters, but 300 milliliters, remember, milliliters are not liters. We need liters. So we have 300 milliliters. We're going to convert that to liters. Every 10 to the third, or 1,000 milliliters, remember, just metric system, that's solution here, is going to give us, well, 1, 2, 3, that gets us 0.3 liters. Before anyone thinks I started off with 0.3. 300 milliliters gets us 0.3 liters. Just move that decimal space to the left 3 spaces when you divide by 1,000. And so these are our numbers. Now we just plug them in. Plug in our moles, 1.966 moles of our solute of NaCl, divided by our 0.3 liters of NaCl solution that we're making. When we divide them, we're going to get a number that is per, or for every 1 liter. When you divide out 2 numbers, the top number is where all your error is, where all your uncertainty is. The bottom number is exactly 1 unit of whatever that bottom unit is supposed to be. So we end up with 6.55 molar NaCl solution. And that's our final answer, 6.55 molar NaCl. So that is the molarity, that is the concentration of the solution we just made by dissolving 115 grams of solid sodium chloride into 300 milliliters of water. Let's do another example. I dissolve 0.721 moles of dextrose. Now this time I've been given moles. 0.721 moles of dextrose into 165 milliliters of water. What is the molarity of the solution that I just made? Actually, this should have been our first example. This is a little bit simpler, isn't it? Here, we don't even have to convert between grams and moles. We've been given moles, which is why you don't even need to know what the formula of dextrose is. You don't care because you've already got moles. You're not going to need grams to moles. You're not going to have to convert grams to moles. And you certainly don't have to convert from moles back into grams because nothing about the unit molarity requires grams if you've already got moles. So we simply fulfill the definition of molarity, which is moles of solute, in this case, moles of dextrose, divided by liters of the total solution. And again, dextrose is going to be a solid, in case that's not obvious. Dextrose is a solid. It stands for glucose, which is a solid at room temperature. So we just take our moles of dextrose, 0.721. Again, we don't even care what its formula is. And we divide by, well, we don't have liters. Remember, milliliters is not liters. So we have to convert. Need to convert. Don't just plug the numbers in. Make sure you are fulfilling the definition of what molarity means. It means moles per liter. So be careful about that. Never forget the definition of what molarity is. And it's not moles. Molarity is not moles. Molarity is moles per liter. It is a drastically different number, and it is a drastically different unit, completely different from moles. You cannot interconvert, or you cannot substitute one for the other. Okay, so let's convert. 165 milliliters. We know that every 1,000 or 10 to the third milliliters is 1 liter. So that's going to be, again, just move the decimal space over 3 spaces to the left, and you've got 0.165 liters of solution. So we put our 0.165 liters of solution. So moles of solute per liters of solution, moles of dextrose per liter of the entire solution. So 0.721 divided by 0.165 gets us 4.37 moles per liter, molar dextrose. And that's our answer. Next, we have another example. This time we're going to start with what we want to make. I want to make a 0.65 molar citric acid solution. Again, depending on what kind of information we have, we're looking for moles. Now, if I had asked you, how many grams of citric acid, I would have to give you either the formula of citric acid or its molecular weight. But since I'm only asking for moles, this is fairly easy because we can easily convert from volume to moles. Remember, molarity, the definition of molarity, the 0.650 here represents 0.650 moles of citric acid for every exactly 1 liter of citric acid solution. Okay, this is a conversion factor. So you can see this in one of 2 ways. Either we can use it as a conversion factor in a dimensional analysis type setup. So what do I have? I have how many moles how many. So that means at the end of my equal sign, I'm going to have moles of citric acid. By the way, note how I abbreviate mole, M-O-L. Molarity is capital M. Moles are M-O-L, lowercase. Totally different units. Moles of citric acid. So I want to figure out how many moles of citric acid I can make. 250 milliliters of water, which again, because citric acid is a solid, we're just going to assume, we're going to make the simplifying assumption that this volume, the volume of solvent in this case, equals volume of solution. You can only do this, again, as a reminder, you can only do this if the solute is a solid. If it's a liquid, you have to add them together to figure out the volume of your solution. The solvent plus the solute equals the solution. In this case, though, we are assuming that the solid has insignificant volume effects. That's the only reason we can get away with doing this. So we have 250 milliliters of solution. So not just water, but solution. This is the result of an assumption. Then we know that every 1,000 milliliters of solution gives us 1 liter of solution. And then we know that every 1 liter of solution contains how many moles? Contains exactly 0.650 moles of citric acid. So what does that give us? So we go from milliliters of solution to liters of solution to, using the molarity given, the conversion factor, we can get to moles of citric acid, which is exactly what we needed. And so from that we get 0.163 moles of citric acid. Now, the other way to do this would be to use a formula, and we're going to use this formula quite often. So this is one of the few times where I'll tell you, if you want to use dimensional analysis, that's great. If you don't want to, the formula is actually going to be just as helpful for you. The formula is this, and I'm going to actually introduce it in the very next slide, but the formula is this: molarity times volume in liters always equals your moles, N, I'll just write moles, moles of solute. This is the formula: molarity times volume equals N, or moles of solute. Okay, so if I want to figure out my moles of solute, all I have to do is take my molarity, 0.650 molarity, molar. In fact, here, I'll write it out like this, and then I'll break down the actual units. Molarity times volume of solution, right? Volume in liters. Well, my volume was 0.25 liters. Remember, we need liters. So 1/4 of 0.65 gives us the exact same number, 0.1625 or 0.163 moles of citric acid. Same result. Why does it work? The reason it works is because the definition of molarity is moles per liter. So if I multiply moles per liter times liters, I end up with moles of solute. This is moles of solute, of course, you know that, moles of citric acid solute. So that's why this works. So molarity times volume in liters equals moles of solute. Volume of solution multiplied by the molarity. Okay, let's continue on. So now this is actually where I introduce officially the molarity times volume formula. Molarity times volume equals N. MV equals N. Molarity times volume equals N. N, of course, stands for moles, just like it did in the ideal gas law. PV equals N RT. N stands for moles. In this case, though, N is moles of solute particles, not moles of gas. The volume must be in units of liters. There will be times when you can actually ignore this, but that's only when you know for sure that your volume units will cancel out in the calculation regardless of what unit you use. Then it's okay to use something else. But if you don't know, use liters. If you're not sure, use liters. Okay, so if we can calculate moles, then we can use this in stoichiometry. In chemistry, generally speaking, you don't put solids together to make them react. For one thing, solids can't react with each other. They need to be loosened up. The atoms inside that make up compounds need to be loosened up. They need to be mobile. So we're going to use solutions very often. We're going to mix solutions, meaning we're going to mix different compounds that have been dissolved in solvents together. We're going to mix those solutions together to watch chemical reactions occur. Remember, back in the module regarding chemical reactions, almost all of those reactions involved aqueous solutions. That's because things don't move around until you dissolve them. So I have a bottle of very concentrated nitric acid. The label says that it is 5 molar. If I pour 7.63 deciliters of this concentrated acid into a beaker, how many moles of sulfuric acid are in my beaker? A, and then how many grams? Okay, so once we have A, we can easily convert from moles to grams to calculate B. So let's do A first. So I have 5 molar. So 5 molar is my molarity. Molarity equals 5 molar. Volume is going to equal, well, it's 7.63 deciliters. But remember, we need our volume in units of liters. So I'm going to convert deciliters. We know that it takes 10 decis to make 1 unit, 1 base unit. Deci means 1/10. So volume is 10 deciliters makes 1 liter. And so that gives us 0.763 liters of solution. So now we have liters, we have molarity, we simply multiply them together. Molarity times volume equals moles. So we take our 5 molar multiplied by our 0.763 liters. Liters will cancel out, we'll end up with moles, and that should give us 3.82 moles of nitric acid, HNO3. If you recall, nitric acid is hydrogen nitrate, nitric acid. So that's how many moles we have of nitric acid. Molarity times volume gives us moles. Now, what if we want to know how many grams of sulfuric acid? Oh, I'm sorry, did I say nitric acid? Wait, what was this? Nitric, was this supposed to be nitric acid or sulfuric acid? I don't remember. It actually doesn't really matter. Since I have 2 sulfuric acids, I'll just change this to sulfuric acid. Sorry about that. I thought for some reason I had nitric acid. Okay, sulfuric acid. So let me just change the formula here. It doesn't actually change anything about our calculation thus far, but it will affect the grams calculation because they have different molar masses. Okay, so I'll go with sulfuric acid. Okay, I guess I have to correct that. So every 3.82 moles of H2SO4, we know that, so if we add all this up, we get 98 grams of H2SO4 for every 1 mole of H2SO4. In case you have any doubts, it's 2 for the hydrogens, 32 for the sulfur, and 4 times 16 is 64 for the oxygens. That gives us a total of 98 grams per mole, H2SO4, molecular weight. .98 grams per mole. So 98 grams per mole. Moles cancel out. We're left with grams. So that's 3.82 times 98. That's going to be just under 380. 374 grams of sulfuric acid in our solution. Well, actually, in our, what was it? 7.63 deciliters of solution. Okay, that's part B. Solution stoichiometry. I think I got a little ahead of myself when I mentioned the stoichiometry before. Now we're going to apply this. So we're going to apply the same formula, molarity times volume equals moles, to stoichiometry. Everything eventually comes back to stoichiometry. Because if we can calculate moles, then we can deal with the chemical equation stoichiometric coefficients, which means we can make some calculations involving reactants and products. This is now going to be the third method we've used to convert other units into moles. We started off with grams to moles, right? That was the first thing. First, we learned grams to moles using the periodic table and the atomic and molecular weights. Then we went from pressure volume to moles using the ideal gas law. Finally, now, third, we're going to go from molarity to moles using molarity times volume equals M. So this is now going to be the third, and for us, the last method that we're going to use to convert to moles. It's all about the moles because chemical equations are all about moles, and because, remember, at the heart of all of this stuff, all this weighing and taking pressures and volumes and all that, at the heart of all of chemistry are tiny little indestructible atoms that can only combine together in whole number ratios because they don't break into fractions. That's why ultimately we have to count particles rather than just rely on weights and volumes. And if we're counting particles, then we need moles, because mole ultimately is a counting number. Regardless of the kinds of measured units that we need to arrive at moles, ultimately moles are simply a count. But it's the measurements that we have to make to get to that count that have all that error built into them. The certainty and uncertainty of the digits. Okay, so let's take our first example of stoichiometry using molarity and converting to moles. I have 117 milliliters of this many molarity silver nitrate solution, and I mix it with an excess of aluminum chloride. Now, the first thing you do with any stoichiometry problem, of course, is to write yourself a balanced chemical equation, because you're going to need those stoichiometric coefficients to be accurate. So I have silver nitrate being mixed with aluminum chloride. So this is a double displacement reaction. So the aluminum will join the nitrate to make aluminum nitrate, 3 of them. That M looks a little funky. I'm going to rewrite it there. This is going to be aqueous, as you know, because all nitrates are aqueous. And then we're going to have silver chloride. This wouldn't be a reaction if both of our products were aqueous. This wouldn't be a reaction. So I better have some kind of precipitate here. So the precipitate, if one of them is a precipitate, it has to be the silver chloride, because we know that nitrates are always soluble. So silver chloride is what we're looking for. We, of course, have to balance this. So if we balance this, we'll get 3 silver chlorides, and that'll give us 3 silver nitrates, which gives us 3 nitrates, but we already have 3 nitrates, so we're good. Now it's balanced. It's getting a little crowded over here, plus 3 silver chlorides. Okay, aluminum nitrate 3, aqueous. There we go. Make it a little bit neater for you. There we are. Okay, so that's our balanced chemical equation. Now, how much silver nitrate do we have? We have 117 milliliters of 0.216 molar solution. But remember, we can't use milliliters because molarity has liters, specifically that unit built in. So I'm just going to go ahead and divide this by 1,000. to convert it to liters. So 117 divided by 1,000 times 0.216, that's going to be 0.117. So that's 0.117 liters multiplied by 0.216 molarity. And that gets us to 0.0253 moles of silver nitrate. So we have our moles of silver nitrate. No need to fuss with the periodic table or adding up atomic weights or anything like that. Just multiply these two numbers, of course, convert to liters, and you've got yourself moles, 0.0253 moles of silver nitrate. We have an excess of aluminum chloride, so we don't have to worry about that. Whenever you have an excess of one of your reactants, or when the quantity of that reactant isn't mentioned, you don't have to worry about it. So we're just going to calculate from moles of silver nitrate, how many moles of precipitate can I theoretically obtain? So our precipitate, again, is this solid. It's a 3-to-3 ratio. So 3/3, 3 moles of silver chloride for every 3 moles of silver nitrate. Well, that's exactly the same number then. 3 divided by 3 is 1. So we end up with 0.0253 moles of silver chloride. And that's our answer to question A, to part A. It's a 1-to-1 ratio. So the moles of silver nitrate ends up being exactly the same number of moles as silver chloride, because every 1 that goes in of silver nitrate, 1 silver chloride comes out. Every 3 that go in, 3 come out. It's a 1-to-1 ratio or a 3-to-3 ratio, same thing. Okay, what will be the molarity of the soluble product? So we have this soluble product here. So what will be the molarity of the aluminum nitrate? Molarity of aluminum nitrate is going to equal the moles of aluminum nitrate over the liters of solution. Well, you might say, well, how do we know how much the aluminum nitrate is? Well, we're going to do the same thing. We're going to calculate the moles of aluminum nitrate. So what are our moles of aluminum nitrate? Well, we can do exactly the same thing. We're going to start with our limiting reactant, which is our only reactant that we have a quantity for, 0.0253 moles of silver nitrate. Let me do this one in a different color. Sorry, let me change colors here just so that it's obvious that this is part B. Let's go with lighter blue. 0.0253 moles of silver nitrate. We know that every 3 moles of silver nitrate, AgNO3, every 3 of these gives us 1 mole of aluminum nitrate. Don't get silver and aluminum mixed up. Be very careful. Silver and aluminum are very different metals. Al versus Ag. So that gives us our moles of aluminum nitrate. That's 0.0253 divided by 3. That's 8.42 times 10 to the -3 moles. So that's the top of our fraction. What about the liters of solution? How do we get that? Well, how much solution do we have? Well, we haven't really been given any information about the aluminum chloride volume. So what I'm going to go ahead and do is I'm just going to assume that the aluminum chloride wasn't a significant volume at all. Generally speaking, when I ask this question, I usually give some kind of a volume of aluminum chloride. I didn't this time. I should have, but since I didn't, I'm just going to go ahead and assume, since no info given for volume, or what we could assume is that the aluminum chloride was a solid and it was dissolved into it was dissolved in the solution with the silver nitrate. In other words, it was solid dissolved rather than having it in its own solution. It dissolved in the water once we added it in the solution, the silver nitrate solution, but we added it as a solid. So that's another thing. Given for volume of aluminum, that's very possible, in fact. Aluminum chloride, assume it was zero solution, zero volume. So what does that mean? That means our total volume then is 117 milliliters for the final, for the ending solution as well. So that means we have our liters equals 0.117 liters of solution. Or I should say our volume, well, yeah, liters of solution is 0.117. It's the 117 milliliters divided by 1,000. So our molarity then is going to be 8.42 times 10 to the negative 3 moles of aluminum nitrate divided by, divided by 0.117 liters, and that's going to equal, how do I always manage to run out of space? 0.072 molar aluminum nitrate, AlNO3. And that's the answer to B. Had we been given a volume and maybe even a molarity of aluminum chloride, but it still turned out to be the excess reagent, we would have taken the two volumes and added them together to get the total volume of the final solution. Okay, let's do another type of molarity and stoichiometry kind of problem. This time we have a specific quantity, molarity and volume given for both the reactants. So that's what makes this a limiting reactant problem, specific amounts of both. So we have calcium, as always, you're going to start with a balanced chemical equation. Calcium hydroxide and hydrochloric acid, these are both solutions, obviously, otherwise we wouldn't be given molarity and volume. This is a double displacement or a neutralization reaction. This is an acid-base reaction. It's a double displacement reaction, but it's also called a neutralization reaction. Calcium will bond to the chlorides. It'll be CaCl2 because it takes two chlorides. That'll be aqueous. And then the other product will be the hydrogen plus the hydroxide, which will be, of course, water. Any neutralization reaction produces salt water, water plus some sort of ionic compound, which we can just call a salt. So calcium chloride is the salt. It's not table salt. It's not sodium chloride. It's the definition in chemistry of a salt is any ionic compound that forms as a result of a neutralization reaction between an acid and a base. So calcium chloride is that ionic compound that forms as the result of a neutralization of calcium hydroxide by hydrochloric acid, or hydrochloric acid by calcium hydroxide, however you want to see it. Okay, so to balance this out, I'm going to put a 2 here just to make the hydrogens even numbered so I can easily balance my hydrogens. Once I do that, I find that I'm balanced. 2 chlorides, 4 hydrogens, 2 oxygens, and 2 oxygens, and 1 calcium each. So there we are. It's a 2-to-1 ratio of hydrochloric acid to calcium hydroxide. We need twice as much hydrochloric acid. All right, so let's do this. First thing I'm going to do is I'm just going to convert both of my volumes directly into liters. So just so it's not an issue for us. 0.045 liters and 0.065 liters. Make sure you know how to do your basic metric system, right? Divide by 1,000, move that decimal place over 3 spaces. That means you have an extra 0 in front of the 0, in front of the 4, in front of the 6, respectively, for each of these volumes. Now I take my volumes in liters for each one. I take my my moles of calcium hydroxide are going to be 0.045 liters multiplied by molarity times volume. Oh, here, molarity times volume, 0.317 molarity. And I'm also going to take my molarity times volume over here, 0.268 molar for the hydrochloric acid, multiplied by 0.065 liters. Here, I'll put it underneath just to save some space. So 0.317 times 0.045 gets me 0.0143 moles. And over here, I have 0.268 multiplied by 0.065. That gets me 0.0174 moles. So which one of these is the limiting reactant? To me, it's clear. To me, it's clear that the hydrochloric acid is the limiting reactant. Now, you don't have to necessarily know this. Like I said, you can always just do go the long way, which is perfectly fine. That's not a judgment. Go the long way, calculate the number of, what are we looking for anyway? In grams, calculate the number of grams of the calcium chloride from each one of the reactants separately and see which one gives you the lesser amount. But because we need twice as many hydrochloric acid moles, that would imply that we need twice the 0.014, which would be 0.028. We only have 0.0174 moles of HCl. Therefore, we don't have enough HCl to completely react with all the calcium hydroxide. The 2-to-1 ratio tells me that I need more moles of hydrochloric acid than I've been given. That's how I know. Despite the fact that I have more moles of hydrochloric acid, it's not double, right? I have more moles, yeah, but it's not double the number of moles. It's just a little bit more. The 2-to-1 says I don't have enough. Nevertheless, let's just walk through this just in case. Let's just walk through it the full way. So we're going to calculate the grams of calcium chloride starting from each one. So from calcium hydroxide to calcium chloride. So we're going to start with moles. We don't need our grams of these reactants, right? We've already calculated moles. Once you have moles of a reactant, don't go back and calculate grams for a stoichiometry problem. You don't need grams to do. Only as if you need that for your final answer for your product or whatever you're calculating, that's when you can convert to grams. So 0.0143 moles of calcium hydroxide. We know that every 1 mole of calcium hydroxide gets us 1 mole of calcium chloride. Now, why are we calculating calcium chloride? Because it's the salt. We're looking for the salt. Calcium chloride in this case is the salt. Remember, it's not table salt, it's salt. Any ionic compound in chemistry can be called a salt as long as it's the result of a neutralization reaction. And then we have to calculate the molar mass. I'll let you do that. I have confidence in you now that you know how to do that. It's 111 grams of calcium chloride for every 1 mole. And of course, I wrote it upside down, so let me just change that around. 1 mole of calcium chloride. Remember, I have to put the moles on the bottom so that they cancel out. That's what actually told me that I was doing something wrong just now. I noticed that my moles weren't canceling because I put grams on the bottom. Now I can see 1 mole of calcium hydroxide cancels out with a mole of calcium hydroxide. We end up with 111 grams multiplied by 0.0143. That's going to be 1.587, let's say 1.59. 1.59 grams of calcium chloride. Now, is this the right answer? We don't know yet. Do not just circle this and say, I got the answer. Remember, you still have to do, in a limiting reactant problem, you have to test both reactants. You have to see how much product you get from each of the reactants in a separate calculation before you know which one is the right answer. So let's continue on. 0.017 4 moles of HCl Okay, so this time we have 2. Every 2 moles, according to the chemical equation, every 2 moles of HCl produces 1 mole of calcium chloride. And then, of course, to calculate grams, it's exactly the same exact information. Nothing has changed about the molar mass of calcium chloride. Periodic table has not changed in the 2 seconds since we last used it. So we just bring that 111 grams down. So we take 0.0174 multiplied by 111 grams divided by 2. Don't forget the 2. Divide by 2, and that gets us 0.966 grams of calcium chloride. So our final answer then is not going to be the 1.59. We reject the 1.59, and this is our answer. This is our maximum theoretical yield. That's the answer to our question. The other one is too big. We reject the larger answer. Reject the big number. Reject the big number, accept the small number. It's like the opposite of negotiating. Well, unless you're the buyer. So we converted our volumes to liters, then we took our liters and multiplied them by our molarities to get moles. And then we converted from moles of reactant to grams of product in each case for each one and compared them just as we always do, just like any other limiting reactant. Once you get the moles of each reactant, the rest of this is just a typical limiting reactant problem. Okay, now let's move on to something else, the dilution formula. The dilution formula is actually just an extension of M times V equals moles. The dilution formula is useful for situations where you're not changing the number of moles, but you are changing the molarity and the volume. The setup is exactly the same form as Boyle's law. I'm not saying this has anything to do with gases. That's not why I'm making this comparison. The comparison I'm making is that if moles are constant, then M times V at the beginning equals M times V at the end. This has the exact same form as P1V1 equals P2V2 for Boyle's law. And for the same exact reasoning, in situations where the moles don't change. And what kind of situation is that? When you're diluting something. How do you dilute something? You dilute something usually by adding more solvent. In fact, typically that solvent is water. If you add more water to a solution, you're changing the volume of the solution. The volume increases while the molarity, the concentration, decreases, but their product is the same. And that's exactly what we mean. N doesn't change in a dilution. That's why this is called the dilution formula. N doesn't change. Number of moles of solute doesn't change. Adding more water doesn't change the amount of stuff dissolved in your water. It just increases the volume and decreases the concentration. It just spreads the solute over more molecules of water. But the amount of solute, the moles of solute, remains exactly the same. So for example, if you have like Kool-Aid or something, and you want more Kool-Aid, you can always add more water, but you're not really getting more Kool-Aid, you're just getting more flavorless Kool-Aid. You're just getting more drink, but you're not getting any more actual Kool-Aid. That's kind of how it is. Or if you have coffee, iced coffee, and you want to make more iced coffee, you can add more water to it, but then you're going to dilute down the flavor of the coffee, and you're just going to have more water. So yeah, you increase the volume, but you still have the same amount of coffee. It's just spread over more water. So the concentration goes down as the volume goes up. Their product remains exactly the same. So that's what dilution is, and that's why this form of the dilution equation works. M times V equals M times V. All we're doing is changing the molarity and volume to new values, but their product will remain exactly the same. The number of moles of solute does not change in a dilution. So let's see, let's actually use this formula. This is very helpful in chemistry because oftentimes you have very concentrated solutions as a stock solution. And actually this happens in real life too. In real life, you'll often buy cleaners, like cleaning solvents. You'll buy them in extra concentrated form so that they don't take up much space. You'll buy a small bottle of concentrated cleaning fluids, But then when you use it, you don't use the fluid just by pouring it onto the dirt. No, you usually dilute it by adding a bunch of water to it. And oftentimes the directions will say, take 1 cup of this cleaning fluid and then dilute it with 2 or 3 cups of water to make an appropriate amount for using at home. So again, that's dilution, and that's exactly how it works in chemistry as well, in the lab as well. So oftentimes, chemical reactants are stored as solutions, as concentrated solutions, not because you want to use that concentration in your experiments, but because it just doesn't, it takes up less space. And then if you need it, you can always just dilute it to get the amount you want. So I dilute my lab stockroom solution of potassium hydroxide from 12 molar, extra concentrated. Any double-digit molarity is very concentrated. I want to dilute this down, so I dilute it down by putting 25 milliliters of it into a large empty beaker. Why do I need a large beaker? Because I'm probably going to have to add a lot of water to it. In fact, you can imagine this like this. You just put a little tiny bit of your 25 milliliters at the very bottom. And then on top of that, you're going to add a whole bunch of water to dilute it down. How much water? Well, the whole volume goes up to 218. So that's what, 207 milliliters of water added. Why? Because not 207, excuse me, 193. 190, sorry for my bad math here. Let me just double check myself. 218 minus 25 is indeed 193. I had it right the first time. Okay, 193 milliliters. Okay, so we add 193 milliliters of water to our 25 milliliters of original concentrated potassium hydroxide solution at 12 molar. What is the molarity of the final solution? So let's use our M1V1 equals M2V2, and just like with the gas laws, we'll make ourselves a little table to help ourselves out. So molarity 1, volume 1, and molarity 2, and volume 2. So let's fill in this table. Our starting molarity was 12 molar. Now, our starting volume was 25 milliliters. I'm going to put 25 milliliters here. Guess what? I am not going to bother converting to liters. Why? Because I know that I'm going to cancel out the milliliter units. Now, again, if you're ever uncertain about whether you can get away with not converting to liters, then just go ahead and convert to liters, because it's better to be safe than sorry. It costs you nothing but a little bit of time to convert to liters. You'll never go wrong if you do that, as long as you know how to convert. But you will go wrong if you don't convert to liters, and it turns out that this is not whatever you're dealing with is not one of those situations where you can get away with that. So if you're not sure, just convert to liters by default. But I'm going to go ahead and save myself a little time here, and I'll show you how the milliliters are actually going to cancel out. Okay, molarity 2. Well, that's what I'm trying to find out, right? So I'm just going to put a big question mark there. That's my question. I don't know. That's what I need to figure out. I need to figure out M2. That's always going to be the way it is, by the way. Later on in the next chapter or module, whatever you want to call it, when we talk about titrations with acids and bases, it's going to be the exact same formula, but there we're going to call it the titration formula instead of the dilution formula. Isn't that nice? We actually get double duty out of this formula. We're going to use it in 2 different ways. Okay, our volume 2 is what? It's 200. We bring the total volume up to 218. So our total volume is 218 milliliters. So I'm just going to set up my formula. Again, just as a reminder, M1V1 equals M2V2. So let's just plug it in. 12 molar multiplied by 25 milliliters equals M2, which I'm going to solve for, multiplied by 218 milliliters. Now, to solve for M2, I'm going to divide both sides by 218 milliliters. Well, you can already see what's going to happen here. When I divide this side by the 218 milliliters, guess what cancels out? Milliliters are going to cancel out. So it doesn't matter whether I use milliliters or liters or not, because either way, the volumes cancel out. What if I had converted to liters? I would have just been canceling out liters and liters. It would have been the same exact thing. The units, whatever the volume units are going to be, if I'm solving for molarity, the volume units cancel. So I don't really care about converting them because it's just going to be wasted effort. Again, if you're not sure, just go ahead and be safe, convert to liters every single time. You won't ever go wrong that way, as long as you know how to convert. And of course you should. The metric system is very important. We should all be learning it. So molarity then, our molarity at the end of the dilution, our diluted molarity is going to be 12 times 25 divided by 218. I'm just going to put the raw numbers here. You can already see that the only unit that's going to be left, by the way, the only unit that remains uncanceled is going to be molarity. So you can see molarity ends up being our final unit, which is what we want because we're calculating molarity. 25 times 12, I believe, is 300, but I don't trust myself anymore. 300 divided by 218, that gets us to 1.38. 1.38 molar. And always list the solute for your next to your concentration. You don't have to specify the solvent unless the solvent is not water, in which case then you should definitely mention the solvent. But if it's water, then it's already assumed. Water is assumed unless you say something else. But you do have to mention the, you have to specify the solute. So 1.38 molar potassium hydroxide. So let's just do a quick common sense kind of check. We started with 12 molar, very, very concentrated. We started with 12 molar. We ended up with 1.38 molar. Does that make sense? Yeah, it does, because we added quite a bit of water. If for some reason you did the math wrong, you made a simple mistake typing into your calculator and you ended up with a bigger molarity than you started with after adding so much water, you should question that, go back and double check your math or double check your work or just recalculate, plug in the numbers. But this makes common sense. We took 12 molar, we added a bunch of water, we should end up with a much smaller concentration, and indeed we do. In fact, you can almost see that it's approximately, 1/10 the concentration. We added approximately 10 times as much volume, 200 versus 225. Then we get about 10% of the final concentration, which makes sense. All right, so I hope that makes some kind of sense to you, but if not, well, let's do some more examples then. Let's do another example. This is actually a more practical, real life. It has one little twist that you would actually have to account for in real life. This is why I do this. Because in real life, you don't typically bring things up to final volumes necessarily. Normally what you do is you figure out what concentration you want, and then you figure out exactly how much water you need to add to get to that concentration. You don't just willy-nilly add a bunch of water and then figure out your concentration. You can, but that's usually not how it's done. So let's see how that works. There's a subtle difference in the wording here. See the word add and see the word add? That means there's an extra step. When you see that, just read the question extra carefully, because there may be, and most likely is, one extra step. Beyond using the formula, you're going to have to do one more little piece of arithmetic that the formula isn't going to tell you you need to do. So be careful. I want to dilute my lab stock solution of 2 molar ferric chloride. Okay, let's just start writing it down. My molarity 1 is 2 molar. So let's just write it down from the very beginning. Down to 0.68 molar. So that's my molarity 2. I have a goal in mind. This time, I actually have an idea of what molarity, what concentration I want to end up with for my ferric chloride. I start by pouring out 18 milliliters of the solution. So that's my volume 1. 18 milliliters into a very large empty beaker. Why? Because I know I'm going to be adding a lot of water. So I better have an empty beaker to hold all that water. How many milliliters. Okay, this time I'm not going to convert to liters only because I want my answer to be in milliliters at the end. If I don't convert my milliliters, I will get an answer in milliliters, and that's perfectly okay because I'm looking for milliliters. Again, if you're not sure, convert to liters, and at the end, convert back to milliliters, and you'll be fine. But in this case, I can already see that that would just be wasted effort on my part, so I'm not going to do it. Okay, so how many milliliters of water do I need to add? Now note, the answer to this question, the answer is not V2. I really want to make this clear. The answer is not going to be V2. We need to calculate V2, but only so that we can figure out how much water we need to add to V1 to get to V2. That's going to be our answer. Our answer, I'm warning you ahead of time because I don't want you to make this mistake. It's very easy to make. In fact, it's very easy to make in lab when you're actually doing this. Our answer is V2 minus V1. It's our change. It's our change in delta. It's our delta V. It's our, well, delta V in volume, not delta V as far as acceleration. Delta V usually means acceleration in physics. Not that I know much about physics. Okay, our change in volume is what we're looking for. The difference between V1 and V2. How much do we need to add to 18 to get to V2? That's what we really need to look for. But we still have to solve for V2 to know that. So again, we plug in our numbers. 2 molar multiplied by 18 milliliters equals 0.68 molar multiplied by V2. Solve for V2 by dividing both sides by 0.68. So V2 is going to equal 2 molar multiplied by 18 milliliters, divide by here, let me write it here, 0.68. I'm writing this off center because I want to show how the units cancel out. So look, notice this. The molarity will cancel with molarity. These are the same unit. And we're going to be left with units of milliliters, which is okay because that is exactly the unit we want. So it's perfectly fine that we end up with milliliters. Now, if we wanted liters, that would be different. Okay, so that ends up being 36 divided by 0.68, or 2 times 18, which is 36, divided by 0.68. That gives us 52.9 milliliters. Okay, that's our V2. Remember, that is not our answer. Our answer is not V2. It's the difference between V1 and V2. So how much water do I need to add? I need to add 52.9 milliliters minus 18. Remember, I already have 18 milliliters in my beaker. I don't need to add 52 to get to 52. I need to add 52 minus 18 to my 18 to get 52. So 52.9 minus 18 is going to be what, 34.1 or something? I'm not sure here. Why don't I just do the math? Use the calculator. 52.9 minus 18. 34.9. So my answer then is 34.9 milliliters of water to be added in order to dilute up to a total volume of 52.9, which will give me a final molarity of whatever it was I was looking for, 0.68 molar. There it is. So this is my final answer. Remember, the answer is not V2. In this case, the answer is not V2 because I'm asking about how much water to add. I'm not trying to figure out the final volume. I'm trying to figure out what I need to do to get to the final volume. And that is a big distinction hidden in a little tiny change of phrase. That's why I want you to watch out for it. Read these kinds of questions carefully. So that's our final answer. That looks like the final answer. There we go. Okay, so now that we've tackled that, let's continue on. Now, this is a big problem here. Not a big problem, sorry. This is a question with lots of concepts built into it. This is one of those combined concept problems, which I think are great, because if you can do this sort of thing, then you really have learned, you know, all the stuff. You're not just like forgetting what you learned in one module as you move on to another. And again, I have my warning here. The volume of a solution and the volume of a gas are two completely different things. Remember, you cannot calculate the volume of a solution from a gas law, and you cannot calculate the volume of a gas by taking molarity. Actually, can you? By taking molarity times volume, at least not the molarity of a solution. You can express the density of gas in molar volume. You can do that, but be real careful about the kind of information you're looking at. Context is everything there. Generally speaking, they are not interchangeable, and you definitely cannot calculate molarity of a solution from any kind of gas law. Gas laws are not applicable to solutions. Just be careful about that. Okay, so this is a limiting reactant, molarity, gas law problem, all in one, and even percent yield. It's got everything in it. And chemical equation reaction problem. This is like 5 different chapters of material in one problem, or one multi-step problem. Should we come back to it? No, let's do it. Why not? You know, you can always pause the video, take a break, and come back if you want. But this is just, it's partly new material and partly just review to make sure you don't forget the old material. But remember, even in this case, the old material reinforces the new material because it's all stoichiometry. Okay, so we have 100 milliliters of a 0.2 molar HCN solution mixed with 200 grams of barium. Given that the gaseous product is stored at a temperature of blah, 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 and a pressure of 1 bar, what will be the volume? Okay, so this is clearly a stoichiometry problem. So what I'm going to do first is I'm going to write myself a balanced chemical equation. I'm going to do it right here to save some space, even though I have some space on the next page. So hydrocyanic acid, or hydrogen cyanide, it's a solution. So I'm going to write this as aqueous. It's being reacted with barium, solid barium. So hopefully you remember what kind of reaction involves a solid metal reacting with an acid. That's right, it's a single displacement reaction. So we have barium cyanide, Ba, and remember barium is a group 2 metal, so it's going to have a positive 2 charge. Barium cyanide plus, and then barium displaced the hydrogen, so hydrogen never goes anywhere by itself, but instead goes as a dimolecular hydrogen gas, H2 gas. What is the physical state of barium cyanide? My suspicion is that it's aqueous. I'm pretty sure this is soluble in water. I could be wrong, but I think most cyanide compounds are soluble in water. If I'm wrong, you can always just message me and say I was wrong, and gain some satisfaction from that, and you will have earned it. Okay, so now let's balance this chemical equation, because the most important thing is to have balanced stoichiometric coefficients. We have 2 hydrogens, so I'm just going to put a 2 in front over here to double my hydrogens. I double my cyanides, which is great because I already have 2 cyanides here. Barium is 1 single barium, so it's 1 mole of barium in the reactant, 1 mole of barium in barium cyanide. So we're good. We only needed to add this 1 stoichiometric coefficient. It's 2 to 1 to 1 to 1. That's our mole ratio. Okay, now what will be the volume of the gas in storage when at 250 kelvins and 1 bar? How do we figure this out? Well, in order to use, this is clearly asking for the gas law, the ideal gas law to be used, but what do we need from a chemical equation that can feed into the ideal gas law but moles? So in this case, we need to calculate n moles of a gas. But how do we do that? Well, first thing we're going to have to do is figure out the moles of hydrogen gas that results from the reaction of barium and hydrogen cyanide. We've been given specific quantities of both, which means we have to calculate the moles of each reactant and then use each reactant to calculate the amount of hydrogen we can make, and then use the lesser amount of hydrogen to calculate the moles of gas. And then we can figure out the volume using the ideal gas law. Okay, so let's do that. let's do part A here. Hopefully I have enough room. I hope I do. Let's find out. Okay, so let's deal with the hydrogen cyanide first. We have 100 milliliters of 0.2 molar. Remember, when it comes to stoichiometry, you're always going to convert to liters. Dilution equation is one thing. You might need milliliters or you might cancel out. But when it comes to calculating moles, M times V equals N, you always convert to liters. So this is 0.1 liters of solution. So I take my moles of HCN. Moles of HCN is going to equal 0.1 liters multiplied by 0.2 molar. And I'm saving space, so that's why if you see me just ignoring sig figs all over the place or trailing decimals and trailing zeros, I should say, that's the reason. I'm just saving space. So that's 0.02 moles of HCN. Okay, so that's my number of moles of hydrogen cyanide. By the way, I could have easily set this up as a dimensional analysis problem right from the very beginning. I could have just started meters, converted to moles of HCN using the molarity as a conversion factor. I could have done it that way. In this case, I really do think the formulas are kind of going to be easier for you. But if you want to do it the dimensional analysis way, you know what? More power to you. I'm happy if you do. Okay, so 0.02 moles of HCN. We know from the chemical equation that it's 2 moles of HCN to every 1 mole of hydrogen. Whoops, sorry about that. Every 1 mole of hydrogen gas. That's our 1:2 ratio. You can see it right there. That's the chemical equation that we're going to use. I mean, that's where we use the chemical equation. So 2 moles of HCN to every 1 mole of hydrogen gas. Okay, since we're not dealing with STP, we can't really go any further without using the ideal gas law. So I'm just going to calculate the moles right now. So that's 1/2 of 0.02, that's 0.01 moles of hydrogen gas. I mean, you can see that, right? 1/2 times 0.02 is 0.01. I mean, you can get your calculator and you can confirm that. Now, barium is in grams. So we have 200 grams of barium. And this, I'm just going to start with dimensional analysis right from the beginning. 200 grams of barium. We know that the the atomic weight, of barium is 137.3 grams. I'm going to pretend I didn't just look that up. I did it. Confession. It's confession time, guys. I looked it up. I don't memorize every single piece of information on the periodic table. And I don't expect you to either, obviously. So 137.3 grams of barium gives us 1 mole of barium. Then we use the mole to mole ratio given in the chemical equation, and it happens to be 1:1. We can almost get away with not doing it, but just for show, just to make sure we know what we're doing, no shortcuts, right? No shortcuts. It's a 1:1 ratio. 1:1 mole ratio. 1:1 mole ratio. Then, well, that's it. Actually, no, that's it. We calculate that. So that's going to be 200 divided by 137. That's going to be about 1.5. 1.46. Well, it doesn't really matter. Whoa, really? Yeah, it's a blowout. 1.46. It doesn't really matter, does it? Because this is clearly the wrong answer, right? We totally reject this. Reject. This is way too big of a number. Look how small that other number of moles of hydrogen is. Reject. So our actual number of moles is going to be this. This is our N value, our number of moles of hydrogen that we are now going to plug into our ideal gas law. And since you know all about ideal gas laws, I'm not going to bother writing out the formula PV equals nRT. I'm just going to write it in the form that we need to solve. So V is going to equal N, come on, N times R times T divided by P, right? Solving for volume, you know you're going to get liters because you know that the units are liters, atmospheres per Kelvin mole in the R value. So at the end, if we want milliliters, we're going to have to do a little converting at the end. That's okay. So we plug in our values. Our N value is the 0.01 moles. That comes directly from here. 0.01 moles of hydrogen gas multiplied by 0.0821, and I'm not going to put units because I don't have enough space. Our temperature was given as 250 Kelvin. That's right in the problem. And I didn't have you convert this time because this problem's long enough, right? I don't think we needed to do some Celsius to Kelvin conversions. Divided by pressure, okay, I did give you bar, sorry. Bar, if you recall, is 100,000 pascals. I'm just going to shortcut this for you. It's 0.987 atmospheres. 1 bar equals 0.987 atmospheres. Okay, so we take our numbers, 0.01 multiplied by 0.0821 multiplied by 250. That's going to get us, and then divide by 0.987. That gets us 0.208. 0.208, and be careful about the units. These are liters of hydrogen gas. This is not liters of solution. This is liters of hydrogen gas. Convert to milliliters by by multiplying by 1,000. And that gets us to our final answer of 208 milliliters, or cubic centimeters if you prefer, of hydrogen gas. And that is our final answer for part A, 208 milliliters. So this was a limiting reactant problem. We had to calculate the moles of both of our reactants, convert from moles to moles of product. We didn't really have enough information for grams. Well, we did, but we didn't really need grams because we wanted to calculate moles. Why do we want to calculate moles? Because we knew that we were going to use the ideal gas law for this gas. Typically, you get gases in moles so that you can use the gas law. We get our moles, whichever one gives us lesser moles, we plug that, we take that number, plug it into the ideal gas law to calculate volume, and then at the end, convert volume to milliliters because that was the requested unit for part A. And that's it, 208 milliliters of hydrogen gas. That's part A. Part B is relatively straightforward. If my percent yield was 68.5%, what was the experimental yield? This is just a plug and chug formula question. We actually have enough room to solve this right here on the same page, but I think I gave myself an extra page here. Yeah, I did. So let's just do this here. So we're going to do part B now. Let's go back. So 208. The only thing I have to do is I have to bring forward my 208. So our theoretical yield, the yield we just calculated, theoretical yield equals 208 milliliters. That was our theoretical. Our percent yield is given as 68.5%. So all we have to do is remember the formula. Percent yield equals the experimental yield, meaning the real life actual yield, experimental yield, divided by the theoretical yield. You always compare whatever's in the denominator. That's the thing you're always comparing to. That's your standard. You always put your standard in the denominator. Multiply by 100 because it's a percent. So we just solve, we plug in, right? Experimental yield is our X value. We don't know what that is. So I'm going to put X over the theoretical yield of 208 milliliters. I know that I multiply by 100 here, and that's going to equal 68.5%. I'm going to divide out the 100. I think most of you already know what I'm doing here, but I'm going to do it anyway. So the 100 goes away, we get 68.5%. 68.5% gets turned into its decimal equivalent of 0.685 equal to X over 208 milliliters. Now, whatever the unit is of our theoretical yield here, that's going to be the unit of our final answer. Let X equal the experimental yield. So X is going to equal 0.685 multiplied by 208 milliliters. And that's going to be, remember, 685, a percent doesn't have any actual units. So we just take our 208 multiplied by 0.685, that'll give us units of milliliters, and that ends up being, that can't be right. Let me try that again. 208 times 0.685, yeah, okay, that makes a lot more sense. 142 milliliters. And so that is our experimental yield, milliliters of hydrogen gas. This is hydrogen, right? Hydrogen gas. That's our experimental yield. So out of a possible 208 milliliters, in real life, whoever was doing this reaction only managed to make 142 out of that 208. That's fine, that's what happens sometimes. Maybe some of it escaped, maybe not all the barium reacted, or whichever one was the limiting reactant. Who knows? Maybe not all of the hydrogen cyanide reacted. Maybe the hydrogen cyanide got out and everybody choked to death. I don't know, because hydrogen cyanide is a deadly poison. Okay, so let's continue on. Using percent by mass data. So sometimes you're given the percent by mass and you need to do some calculations with it. I mix 50, and again, this is going to be another stoichiometry problem. So I mix 55 grams of a 12% M over M, 12% by mass or 12% by weight, sodium sulfide solution. So again, since we have this is a stoichiometry problem, sodium sulfide D, so there's no oxygen, so it's just sulfur with its 2 negative charge. Sodium sulfide solution tells us it's a solution, plus hydrochloric acid, HCl. I think we've looked at this chemical reaction before, and I mentioned it creates hydrogen sulfide gas, a stink bomb gas, the smell of rotten eggs. So this is a double displacement reaction. We make sodium chloride, and I'll just balance it. It's going to be I'll do it later. Sodium chloride, of course, is aqueous, and hydrogen sulfide actually turns out to be a gas. If you do this at any appreciable temperature above room temperature, hydrogen sulfide will actually evaporate into the air. And we're going to go ahead and balance this. There we are. How many milliliters of product gas will be produced at STP? That makes things so much easier, because if you remember that it's the molar volume of an ideal gas at STP is always 22.4 liters, you know that this makes things a lot simpler if you've memorized that value. If not, then you're just going to have to invoke the ideal gas law once again. Okay, so let's get to the new stuff first. 55 grams of a 12% by weight solution. So 55 grams of solution. Okay, so you can do this one of two ways. 55 grams of solution. We know that a percentage just means 12 grams of sodium sulfide is equal to 100, remember, percent, 100 grams of whatever the total is. Well, the total is the solution. The solute is on top, sodium sulfide, the solution is on the bottom. So 100 grams of solution gives us 12 grams of solute. So you can do it that way. And then you can work this out by saying, okay, well, if that's the case, I can just continue on. What is my molar mass of sodium sulfide? It's 46 plus 32. That's going to be 78 grams of sodium sulfide. That's 2 sodiums and 1 sulfur. That's 46 plus 32. 23 times 2 is 46 plus 32, 78. Yeah, okay, 78 grams of sodium sulfide, gives me 1 mole of sodium sulfide. And then, using the chemical equation, I know that it's a, it's a 1-to-1 ratio, 1 mole of sodium sulfide to every 1 mole of hydrogen sulfide gas. It's a 1-to-1 ratio. And because I know this is at STP, I know that every 1 mole of H2S gas is going to be exactly 22.4 liters of H2S gas. That's the at STP part of this. Again, if you don't remember that, that's okay. Just plug in your standard temperature, 273 Kelvin, plug in your standard pressure, 1 atmosphere, into the ideal gas law, and out will pop that 22.4 liters. Okay, so we take 55 times 12 divided by 100 divided by 78 times 22.4. That gets me 1.90 liters. How many milliliters? Okay, 1.9 liters of hydrogen sulfide gas. I'll convert it if it turns out to be the right answer. Do we know if it's the right answer yet? No, we have no idea. We still have to do the other reactant. By the way, just as an alternative, what happened here? What is this? Here we are. Okay, as an alternative, we of course we could have used the formula 12%. So 55 grams of a 12% sodium sulfide solution. We know that the 55 grams is the mass of our solution. We know that the ratio of the X number of grams of solute, of sodium sulfide, we don't know what the mass of sodium sulfide is. We just know that X grams of sodium sulfide per 55, so 55 is the same thing as 12 grams to 100 grams. Now we can solve. If you really want to do it that way, you can. And you'll get exactly the same number. You'll get 100 divided by 55 times 12. Oh, wait, I have it backwards. I have it upside down. Wrong way, wrong way. Sorry about that. 55 times 12 divided by 100. And you can already see the math is working out exactly the same. 55 your grams equals grams of sodium sulfide. And then from there, you convert to moles, just like we did above. All the rest of it is exactly the same. You can work that out that way if you prefer. Personally, I think it's a lot easier just to use the percentage as a conversion factor between grams of solute and grams of solution. It's always, whenever it's a percentage, remember the number on the bottom is 100. By definition, a percent has 100 on the bottom, and then whatever the number of the percent is, 12, 13, 25, whatever it is, that's the number that goes on top. Okay, now let's do the hydrochloric acid. This is going to be a lot easier because all we're going to do is we're going to take the volume, the liters, we're going to convert to liters. So that's 0.05 liters. And we're going to multiply that by 0.3. So 0.0500 liters of solution of hydrochloric acid multiplied by 0.3 molar HCl, that's going to give us 0.015, if I'm not mistaken, 0.015 moles of HCl. Let's see, let me double check my math. 0.05 times 0.3, 0.015, yeah. 0.015 moles of HCl, and then we use that to calculate. We know that it's 2 moles of HCl for every 1 mole of hydrogen sulfide, H2S. Okay. And then same result, right? 1 mole of H2S is 22.4 liters of H2S at STP. Remember, we can do this because we're at standard temperature pressure. A mole of any gas, any ideal behaving gas, is going to occupy 22.4 liters. Okay, so we take 0.015, divide by 2 times 22.4. I got 0.168. 0.168 liters of hydrogen sulfide gas. Well, clearly, I'm glad I didn't waste my time converting the top number, because that number is going to be rejected now. So we reject, after we found out about this, we reject the big number. As always, with limiting reactant type problems, you reject the bigger quantity of product and you accept this quantity multiplied by, again, 1,000 milliliters, convert to milliliters, and we end up with 168 milliliters of hydrogen sulfide gas as our product. So that is our maximum theoretical yield of hydrogen sulfide gas in milliliters. Okay, continuing on. Now, here's a very common issue in lab. Oftentimes, you're going to be following a lab procedure that's going to call for a certain molarity of acid or some kind of solution, but all you have in lab is something with a percentage by mass or even percentage by volume label. So in this example, the lab procedure for your experiment calls for 0.450 molar sulfuric acid. Don't worry, there's no actual experiment, all right? This is hypothetical. This is just a question scenario. So 0.450 molar sulfuric acid is what you're supposed to use, but all you have is a bottle that's labeled 28% sulfuric acid. This happens all the time. It really does. So because of that, what are you going to do? First of all, I'll tell you right now, if it's 28%, if it's a double-digit percentage, chances are it's very concentrated, probably a lot more concentrated than what you need. So you're more than likely going to have to dilute it down by adding a bunch of water. The question, though, is how much water? Because how do you relate 28% to 0.45 molar? Well, you're going to have to do some calculations first. But just to start off, you decide, okay, well, maybe you'll just dump 25 milliliters of this concentrated solution into a big empty beaker, because you know you're probably going to have to dilute it. But you're going to get a big beaker because you don't know exactly how much water you're going to need to add to dilute it down. So you put 25 milliliters into your empty beaker, then you hit the calculator and your pencil and pen paper, and you start to work out some numbers here. So let's do that. How much water should you add? That's the question, to get the right concentration. So let's start by putting all of our information into a table. The first thing we're going to, actually not really a table, the first thing we're going to have to do, our first step is to convert our percent to molarity. This is our first thing. We're going to take the compound unit percentage, we're going to take that definition of what that percentage means, and we're going to convert it to the definition of molarity. Well, what is a percentage? What we're saying when we say it's 28% sulfuric acid by weight, what we're saying is that for every 28 grams of pure hydrogen sulfate, we have how many grams of solution? Well, what's the denominator in any percentage? The denominator in a percentage is always, by definition, must be exactly 100. This is an exact number. It's not a measurement. By definition, a percent is a number over 100. It's a fraction over 100. Remember, these two circles here in this line, oh, geez. Sorry about that. Here, let's go back. Those two circles in that line represent 100 per 100. By definition, it's built into the definition percentage. If that's one thing I can get you to believe and carry with you after this class, that's going to be it. Okay, that is the definition of percent. We want to convert from the definition of percent to the definition of molarity, which is what? Which is moles of H2SO4 to liters of solution. So we want to convert. The way we're going to do this is we're going to convert the numerator to the new numerator, and we're going to convert the denominator to the units of the new denominator. In other words, we're going to convert from here to here to figure out what this is, and we're going to convert from here to here to figure out what this is. Once we have those two numbers, green and purple, or those two question marks, we're going to divide the top one over the bottom one to get our molarity. Once we have our molarity, we can use the dilution formula, just like we would use any molarity, as if we had been given molarity from the very beginning, but one step at a time. So this is step one, is to try and figure out what molarity, how to convert from percentage to molarity. Okay, let's do the numerator first. Let's do the top first, which is, maybe I should stick with the color coordination, right? Top first, just for no other reason than just because it's the top. Okay, so we want to convert from 28 grams to moles. 28 grams of H2SO4, we're going to convert that to moles of H2SO4. Well, we know that 98 grams of H2SO4 gives us 1 mole. And again, if you don't believe me, just add up all the atoms, all the elements in H2SO4, you will see that their atomic masses sum up to 98 grams. We already did this before. This is the second time we're using sulfuric acid, and the second time we're converting to moles. So 28 grams of H2SO4 divided by 98 will give us the top number, our number of moles. 28 divided by 98 is going to be just about a quarter. 0.286. 0.286 moles of H2SO4. That is the top of our definition. Now the bottom. Now we're going to convert from 100 grams of solution to liters of solution. Now you might say, well, how do we go from grams to liters? Do not assume that a solution has the same density of as water. That is not true most of the time. Now, sometimes you can assume that, but you have to be told that you can assume that. Otherwise, do not assume that a solution is the same density as pure water. Pure water is 1 gram per milliliter. This solution is not 1 gram per milliliter. I can assure you because I gave you the actual correct density. Okay, so now we're going to do the bottom conversion. We're going to convert 100 grams of solution to liters of solution. How do we do that? We're going to use the density. We know that every 1.2 grams of this solution, and that is given right here. This is the information we need. It is told to us. It has to be. Otherwise, I can't expect you to answer this question. This is our density. We use the density to convert from grams of solution to milliliters of solution, and then milliliters to liters. Of course, unless you have the density already in liters, then good for you. So every 1.2 grams of solution is going to give us exactly 1 milliliter of solution. But we don't want milliliters, we want liters. So let's convert. Every 1,000 or 10 to the third milliliters is 1 liter of solution. Okay, so all of our units cancel out except for liters of solution. So we take our 100, divide by 1,000, that's 0.1. 0.1 divided by 1.2 is going to be 0.0833333. 0.08333, that should be enough. Liters of solution. That is our bottom number. All we have to do now is fulfill the definition of what molarity is. Moles here divided by liters here. 0.286 divided by 0.0833. And I'm going to put in a nice neutral dark blue color. So now we take our 0.286 moles, divide by our 0.0833 liters. And that's going to equal, no, I don't really, should have drawn it first. 0.286. I already have the number here. I'll just multiply the inverse of that. I get 3.43 molar sulfuric acid, H2SO4. That is not our final answer, right? That is just on the way to the final answer. Remember, the question was not what's our molarity. The question was how much water should we add in order to dilute this 3.43 molar solution to 0.45. Now that we know the molarity, we can use the dilution formula, because the dilution formula is easy enough to use once you have molarity. To be honest, you can use the dilution formula even with percentages. The only problem is you wouldn't know. If you use the percentage, you wouldn't know what your final molarity is. And you were specifically aiming for a particular molarity. Do I have enough? Oh man, okay, I don't have enough. I don't have an extra page here. So what I'm gonna do is I'm gonna have to erase some of this. That's okay, just rewind if you want to write all this down. So, okay, now that I know that was step one. All of that was step one. Step two now is to take this molarity, the 3.43, and use it plug that into the dilution formula. So let me just go ahead and erase all of this stuff. Sorry about that, but I didn't give myself an extra white space to do part B, or to do the rest of the problem. I'm gonna have to just sort of erase, make some space. Okay, I don't want any confusion about any of this other junk left over. Okay, so let's take that and plug it in. So now we can make our table. Now that we have the information we need, let's make our table. We have molarity 1, which is our 3.43 molar. That's what we just calculated. We calculated our starting molarity. This is the molarity that is represented by the 28%. Our 28% equaled was equivalent to the 3.43 molar. You can actually look this up and you'll see it actually. You can, if you actually wanted to shortcut this, or if you just needed the information, Google is your friend, you could have actually just looked this up. Of course, I don't want you to do that. I want you to be able to calculate this yourself. What if the information were not available? What if it were for some acid that wasn't as popular as sulfuric acid? Then you'd have to calculate it. Molarity 2 is what we're aiming for. That's our 0.450 molar. We know our molarity 2 because we have it in mind. That's what we're gunning for. That's our target. Volume 1 is 25 milliliters because we chose that, right? Or you chose that in this hypothetical example. You decided you're going to put 25 milliliters of the concentrated acid into a beaker so that you can dilute it with whatever amount of water is required. And then our volume 2, of course, is what we have to figure out. But again, volume 2 will not be our answer because of the word add. Add. Whenever you see the word add, just be very careful. Sometimes it is the total volume, but most of the time when you see the word adding water, it's probably not, V2 is not your answer, but it's the difference between V2 and V1. So be careful. So what I'm going to put down here as a note for the final answer is actually V2 minus V1 equals my final answer. Okay, just as a reminder. Okay, so what is V2? Well, I think by now you know how to solve simple algebraic formula. So I'm just going to write V2 is equal to M1V1 divided by, wait, what did I just do here? Yeah, M1V1 divided by M2. Here we go, M2. So that's going to be 3.43 molar multiplied by 25 milliliters. Again, I don't care about the milliliters because I probably want my answer in milliliters, so I know exactly how much to measure out. Divided by M2, which is 0.45 molar. You can already see here that 3.43 divided by 0.45 is going to be about 7 times. In other words, we're probably going to need about 7 times our initial volume of total solution. So 3.43 divided by 0.45 is about 7.6, oh, even more than 7 times, multiplied by 25 milliliters. Whoa, really? Okay, oh, no, that's only 190, never mind, okay. That's 190, let's say 191. 191 milliliters. But remember, that's our volume 2, 191 milliliters. So our answer is not going to be 191 milliliters, but instead is going to be the 191 milliliters. Let me do this in green. 191 milliliters minus 25, which is going to be 166 milliliters, if I'm not mistaken. Let me just double check that. 191 minus 25. 166 milliliters of water to be added. Water to add to the initial 25 milliliters. Okay, so be careful about that. So we need to add 166 milliliters, bring that 25 milliliter volume up to 191 with a bunch of water with no solute in it, and that will bring our molarity down from 3.43 to 0.45, 3.43 to 0.45. Raise the volume, lower the concentration. As long as you're not, unless of course you add more of the same solution, then that's just going to increase the volume and keep the same concentration, which doesn't make a lot of sense. That's not a very useful prospect for you. Okay, so hopefully these complicated, long complicated examples are not scaring you off. It's a lot of number crunching, but again, if you understand what these units are, how they're guiding you, and if you understand how to convert between the definitions, remember, all I did in this entire problem was just look at the definitions of what a percent is and what molarity is, and then I just converted the numerator and denominator from the units of one definition into the required units of the other definition. These definitions of concentration are simply unit conversions. They're exactly the same thing we've been doing since day one in this class. All we're doing is unit conversions. It's just a matter of the context surrounding that unit conversion. That's all it is. If you see it that way, all of this will become just, I can't say child's play, but it will become a lot easier. I will say that. It won't be, I can't guarantee it'll be easy, but it will be easier, a lot easier, if you see it that way. But if you remember, let me just say this, if you're trying to memorize this as a bunch of procedures from step 1 through step 10 in order, like when I see this problem, I do step 1, 2, 3, 4, you can't possibly do it. Nobody can memorize this many procedures for this many different kinds of problems. Any little thing that changes about the problem is just going to completely throw you off. Don't do it that way. I mean, at the beginning, it's fine. You know, if you need to like look at it in an organized fashion, step 1, step 2, that's great. But just as you do a few of them, start to understand that all you're really doing are unit conversions. You're just letting the units guide you from one unit to another. That's all you're doing. Grams to moles, moles of this to moles of that, moles of that to moles of, to back to grams again. That's all you're really doing. Going from grams, that's all we did here, right? We went from grams of H2SO4 to moles of H2SO4. We went from grams of solution using density, which we learned in module 2 or 3. We use density to go from grams of something to milliliters of something. And then we converted from milliliters to liters using the metric system. We have not done anything new so far. Not fundamentally. We are simply mixing and matching all the different ways of converting that we learned from the very beginning. Okay, pep talk over. Let's get back to work. Okay. Calculating percent by volume. So percent V over V. Percent V over V. Often shorthanded V over V, percent. Okay, so this is going to seem like a very easy example now. But there's something critical to remember about these. When you're doing percentages, remember the bottom, the denominator, the bottom number is the total of the volume of the solute and the solvent. Extremely easy to forget. Even I have made this mistake myself after constantly warning students not to do it. I myself have done this. Very rare, but I do. So I mixed 35 milliliters of glacial. Glacial is just pure acetic acid with 165 milliliters of water. Okay, so my solute, my volume of solute, the top number is 35 milliliters. By the way, note it doesn't make any difference what volume unit you use, as long as the top and the bottom volume units are both A, volume units, and B, the same unit, they'll cancel out, and that's all you need for a percentage, for the units to cancel out completely. So volume of solute is 35 milliliters of acetic acid. The volume of solution is what? Don't say 165 because it's not. I bet some of you are thinking it. I know, because that would be my first instinct, would be to add 165 and put it on the bottom, but it's not. It's 165 milliliters plus, so that's our volume of solvent, plus solute of 35 milliliters. In fact, I kind of made it so that they fit together to give you a whole number, or a number divisible by 10, 200 milliliters. That is our volume of solution. So be careful. So 35, so we just fit the definition of percent volume, percent by volume. Percent V over V is going to equal 35 milliliters divided by 200 milliliters. Of course, all percentages require you to multiply by 100. So that's going to be half of 35%. That's going to be 17.5%. And always write the identity of the solute, which in this case is acetic acid, which I'll just write as HC2H3O2. I'll just write the formula because it's a lot easier than writing out acetic acid for me right now. 17.5%. So this is our solution. The crux of this is this. This is the one thing I want to warn you away from. Don't say 165. Don't just take the volume of the solvent as your volume of solution when it comes to mixing two liquids together. Liquids both have definite volume. And even though their volumes are not always additive, perfectly additive, meaning you don't always get exactly the sum of the volumes when you actually mix two liquids in real life, it's okay. We're going to assume for our purposes that you do. I'll give you an example of what I mean. I once took about 40 milliliters of, I think it was acetone, and 40 milliliters of, I don't remember if it was distilled water or ethanol or methanol, I don't remember. But I took two liquids that dissolved well with each other. I added 40 milliliters of each, and instead of getting 80 milliliters total, I got about 78 milliliters of solution at the end. That's because when they mixed, their volume changed. They actually reduced volume. Because they mixed so well, they actually kind of drew closer together. The molecules of the different substances actually sort of just squeezed together. The resulting solution took up less space. Nevertheless, we're not going to try and predict that. We can't predict that. That's just something that's empirical. You're just going to have to observe that if you want. There are workarounds for that in real life. In lab, you use what are called volumetric flasks in order to overcome that sort of uncertainty about total volume. But we're not going to do that. So, or that's not going to be part of our hypotheticals necessarily. I might work it in, who knows. Okay, so anyway, percent volume, here's another percent volume over volume or percent by volume formula. Use, I have 40 milliliters of nitric acid solution. The label states that the concentration is 18% by volume. How many milliliters of pure liquid nitric acid are dissolved in the water? The implication here is that if I have a nitric acid solution, it's 40 milliliters of nitric acid mixed with water. That's the total solution. So my volume of solution is 40 milliliters. I'm going to write 40 milliliters of solution. I'm going to use my percentage as a conversion factor. So what I'm going to do is I'm going to say, well, I know that it's 18 milliliters. Again, I'm choosing the unit milliliters because it's convenient for me because I've already got milliliters. 18 milliliters of nitric acid. Oh, this is where the nitric acid was. Okay, for every what? 100 milliliters. Remember, by definition, the percent means 100 on the bottom. So 100 milliliters of solution. Solution represents the whole. Nitric acid, HNO3, represents the part. Remember, all percentages are part divided by whole. We're not doing anything different from that original definition. We're just specifying in what's the part, what's the whole. In this case, the solute is the part, the solution is the whole. So 18 divided by 100, you don't have to multiply by 100 if you do it this way. You can already see the units are canceling. So 40 divided by 100 is going to be 0.4 times 18. If you're using the formula, you'd solve it exactly this way. You do the numerically, it works out to be exactly the same thing. 7.2 milliliters of pure liquid HNO3 are somewhere mixed, or somewhere, but are in there mixed in with the water. If somehow you were to evaporate away all the water, and you really couldn't, but if you were to somehow distill this mixture of nitric acid, and I don't recommend you distill acids, but if you were very carefully, slowly to try and distill most of the water, I don't think you could get a perfect separation. You would be left with about 7.2 milliliters of nitric acid, assuming, you know, you were able to do an efficient distillation. I believe nitric acid has the higher boiling point, so you'd evaporate away the water. I could be wrong about that. I don't remember the boiling point of pure nitric acid. You can look it up, fuming nitric acid. 7.2 milliliters out of 40 for the solution, 7.2 milliliters are pure nitric acid. The other, so, well, here's the next question, or here's another question that could be asked. So, and this is not meant to be hard at all. How many milliliters of water? Well, you don't even have to do any real calculating other than some subtracting, right? If 7.2 is hydrogen nitrate, and we have 40 milliliters total, well, 40 milliliters minus 7.2 milliliters, this is total solution, this is HNO3, the difference must be water, right? I mean, at least presumably, we're making the assumption that, you know, liquids don't interfere with each other's volumes, that they're perfectly additive, which for our purposes, just go ahead and assume that. Okay, now we have parts per million and parts per billion. These are usually the kinds of information you get from government websites about safety of lead in drinking water or something. Part per million, it's exactly like percentage. I'm actually going to explain a little bit more here than I did up earlier. I know this is looks like a repeat of the slide I had earlier, but I do have a little bit more to add here. Okay, part per million works exactly like percentage. Just as in a percentage where you take some kind of unit, usually grams, divided by grams, and you multiply by 100, grams of solute divided by grams of solution times 100, percent literally means per 100. So what does part per million mean? Well, it just means grams divided by grams times not 100, but 1 million. That's the only difference. Part per billion, take the unit of solute, divide by the unit of solution, and multiply by 1 billion. What units? Generally speaking, mass units. You can do a part per million, part per billion by volume instead. Usually you'll label it so. For example, ppmv would be part per million by volume. ppbv would be by part per billion by volume. That's what the V stands for. It stands for volume. Generally speaking, though, it's understood that if you don't say anything like that, it's by mass. Another way to represent these, by the way, is to convert your solute to units of milligrams and to convert your solution to units of kilograms. Milligrams over kilograms gets you per million. We talked about that already. In fact, I think I already mentioned this, didn't I? Okay, well, anyways, that was in anticipation of this slide. So I think I've already said all that. Let's actually get into some examples. I think you get the idea. Okay, ppb, part per billion. The federal government sets a limit on the amount of lead that can be in drinking water to 15 micrograms per liter of water. This is per liter of water. Now, bear in mind, again, the micrograms of lead ions in the water isn't going to have any kind of significant effect on the volume of the water. So for all intents and purposes, the liters of water, or the mass and the volume of water are going to be assumed to be the mass and or volume of the solution, because 15 micrograms of lead is not going to change anything. All right, it's not going to change. That's 0.0000015 grams. We're not even going to measure to that level as far as grams go. So don't worry about it. So I'm just going to write that, assume that mass and or volume in these cases of solute is effectively zero. So ignore that. Just take the units for the solute, for the water on the bottom as your solution. So don't worry too much about whether it's water solution. As far as we're concerned, are one and the same. Okay, so the federal government sets a limit. So 15 micrograms per liter. What is this amount expressed in parts per billion? Okay, so let's remember, what is the definition of part per billion? One way to figure out parts per billion is to get the micrograms of solute divided by kilograms of solution. Actually, this is pretty much done for us, isn't it? I think it's the same number. Let's see, but let's just work it out and make absolutely sure. Yeah, it is, right? 15 micrograms of lead. So the top number is already micrograms, 15 micrograms of lead, 2 plus or 4 plus. I assume it's 2 plus, but what about the solution? Well, we have 1 liter of solution. 1 liter of solution. What is that in kilograms? This is water, right? H2O or water. Again, the density is not really going to be affected by a mere 15 micrograms of lead. So for all intents and purposes, 1 liter of solution is going to be, I'm going to take the long way, even though I don't really need to, but just to explain it, we have 1,000 milliliters per liter of water. Then we know that the density of water is 1 gram per milliliter. And then we know that it's 10 to the 3rd grams for every 1 kilogram. Now, if you notice, all of these thousands are going to cancel out. 1,000, 1,000, they cancel out. And so what we end up with is 1 liter of solution is 1 kilogram. 1 kilogram. So a liter of water is a kilogram of water. So we probably didn't need to do all that, but I wanted to make it clear. So we have 1 kilogram of solution. So we fulfill our definition. So 15 divided by 1 is 15 parts per billion. And that is our answer. It's actually effectively the same number. They are expressing this in parts per billion, only they're using SI, standard scientific units, to report it. These are SI units. Part per billion and part per million and percentage are not SI units. They are not official scientific international standard units. They are not accepted as international standard units. So part per million, part per billion, these are not scientifically official, but they are governmentally official. So 15 parts per billion. Not a very hard problem, is it? Let's do another one. Here's a part per million example. I don't know why it says example 2. This is our first example. I have 2.8 times 10 to the -6 grams of chromium ions dissolved in 135 milliliters of water. What's the concentration in parts per million? Now, the definition, again, this is all about definition. Part per million definition. Definition of part per million is, you can either use grams divided by grams times 10 to the 6th, or you can use milligrams per kilograms without the 10 to the 6th. Let's try it both ways. We should get exactly the same answer. So we already have grams. So let's just take our solute is chromium, obviously. That's what's being dissolved in the water. 2.8 times 10 to the minus 6 grams of chromium. How about the 135 milliliters? Well, we know that 135 milliliters of water is 135 grams of water, and thus solution. Remember, 1 gram per milliliter. In this case, remember, when you're talking about parts per million, parts per billion, these are extremely tiny, tiny concentrations. They're so small that they have negligible, insignificant effect on the density, the volume, and the mass of the overall solution. Because they're so insignificant, unless you go out to like the 100,000s to 1 millionth decimal place, and we're not going to do that, they really don't matter. Okay, so we take 2.8 times 10 to the minus 6 divided by 130, so that's grams divided by grams, but again, we multiply by 10 to the 6. But wait a minute, what happens if we do that? Hey, times 10 to the minus 6 and 10 to the positive 6, well, doesn't that just equal 10 to the 0, which is 1? Yeah, so these actually go away. The 10 to the 6 and the 10 to the minus 6 cancel out. So our answer is going to be the 2.8 divided by 135. You don't have to cancel them out. You can type it all in and you'll see it works out just the same way. We end up with 0.021. So our final answer is 0.021 parts per million. Actually, if we wanted to, we could do this in parts per billion. It would be 1, 2, 3. It would be 21 parts. Wait, no, it would be the opposite. Sorry, we'd be moving the opposite way. If we wanted to do parts per thousand, it would be 21 parts per thousand. Unfortunately, people use PPT to represent part per thousand or part per trillion, which is very confusing. That's probably one of the bigger complaints about using parts per terminology is that sometimes you don't even know what it's a part per, because you can use the same letter for thousand and trillion. Let's not delve into that debate. Let's just accept this the way it is. 0.021 part per million. This is, after all, a question about parts per million. Let's do it the other way. Let's convert to milligrams and then kilograms of the other one. 2.8 times 10 to the negative 6 grams of chromium or anything else. We know that every 1 gram is 10 to the 3rd milligrams. So that's 10 to the 3rd times 10 to the minus 6. That's going to be 2.8 times 10 to the minus 3 milligrams. 10 to the 3rd, 10 to the minus 6. That's negative 6 plus 3. That's negative 3. And then on the bottom, we're going to have 135 milliliters of water, or solution in our case, solution. We know that every 1 milliliter of water is 1 gram. We know that every 1,000 grams is 1 kilogram. So that's going to be 135 divided by 1,000 is 0.135. You know what? Tell you what, why don't I write it this way? Sorry, 135 times 10 to the negative 3 kilograms. Why did I do that? Because when I divide these by each other, what am I going to get? The 10 to the minus 3s are going to cancel out. I'm going to get, what do you know? 2.8 divided by 135. The exact same thing I got over here. It's going to be the same number. Right back where we started again. So there you go, 0.021 parts per million. Milligrams divided by kilograms, or grams divided by grams times a million. Remember, if you're doing straight up grams, you better multiply by 1,000,000. Otherwise, you're gonna get some funny looking numbers, really tiny numbers. But if you use the milligrams and kilograms, remember, these already have the units built in. 3 and minus 3 and 3 is 10 to the minus 6. That already equals per million, 1 per million, or 1 in a million. So you don't have to do anything else to that. The units take care of it for you. But if you're using units that cancel, then you'd better multiply it by the 1 million, because the units aren't going to do the work for you if they just cancel out 1 to 1. Okay, that is all the units, the concentration units that we're really going to deal with. The only unit we really didn't work with was molality, and that's mainly because we're not going to bother trying to calculate molality. We're simply going to take information given in molality, and we're simply going to stick it into a formula to calculate something else. So we're not going to ever have to figure out molality or convert back and forth between molalities. It just isn't used enough, and it's just not worth our time. So we will look a little bit more at molality next time in relationship to colligative properties, freezing point, depression, boiling point elevation, osmosis. Oh, well, we won't use molality with osmosis, but we'll look at colligative properties. After that, we'll also look at different types of solutions and different ways of categorizing solutions. And then that'll be it for module 13. There's only a little bit more calculation up ahead. A lot of it up ahead is conceptual, but there is one very, very important point about the Van't Hoff factor that you will have to sort of come to grips with, because it's a very critical point to understand about dissociated molecules and ions in solution. So Van't Hoff factor, V-A-N''T-H-O-F-F, Van't Hoff. So we'll take a look at that next time. I hope this video was informative. I hope these examples were informative. I hope you could, if you had any trouble, go back, watch the video again, work through them step by step again. This is a lot to take in, I know, but just keep in mind, use the stepwise way I go through this as a crutch, but eventually my hope for you is that you can be flexible in your understanding, letting the units and the definitions of these compound units of concentration guide you to doing these problems without having to go, step 1, convert this, step 2, convert to that, that sort of thing. The goal for you is to be able to handle any problem involving these units, regardless of the wording, regardless of the format. Okay, let me know how it's going with you. Let me know if you have any questions or trouble. I will see you in the next video. Take care, everyone.